So I got to show those. Right? I got springs. I haven't even read the question, but I see springs. I see a kind of concurrency. What do I know about springs? Uh-oh. They're not in series and not in parallel. That's okay. But I do know F equals kx, which is Hooke's law, should probably come into play in this problem. Find the equilibrium, some force x, some force y, plus Hooke's law. You with me? Haven't read the question yet. All right, let's read the question. 15-kilogram block is suspended by springs AB and AC. Stiffness of spring AB is 1250. AC 1500. What is the unstretched length of each spring once weight is removed? Okay. Free body diagram at A. Here it is. I should have some force here, which is the weight. What's the weight? Huh? Yeah, don't forget 15 times 9.81, which is 147.15 newtons. What goes on a free body diagram are forces. Weight is a force. Mass, kilograms, is a mass, not a force. So you must convert to forces. All right. I will have some force this way, FAC, and I will have some force here, FAB. I will put in my coordinate system. Lucky for you, we only use one. That is the XY coordinate system. Once I do that, I need to put angles in. So I need this angle, theta, and I need this angle, alpha. Now, I can calculate alpha and theta by doing some trig. I'm not going to do the trig. I'm going to use slopes, just to get you kind of used to slopes. So, here's this. Here's that, here's this. This angle is theta, which means that angle is theta, right? First thing I'm going to do is I'm going to say LAC is equal to square root of 1.6 quantity squared plus 0.4 quantity squared. What did I just do? I took the millimeters and converted it to meters. Well, why the hell did you do that? Can I use 1600 and 400?
No.
Why not?
Because this is millimeters and the Hooke's formula requires meters.
The what?
Hooke's formula requires meters, not millimeters.
No, it doesn't.
They're not SI units.
It doesn't require millimeters or meters. It can use any units you want. But why am I converting? Well, look at the K values, newtons per meter. Not only that, what's this guy in? 9.8 meters per second squared. So if I don't convert, I'm going to have mixed units. Pay attention to details. So this is going to give me 1.649. LAB is going to give me square root of 0.4 quantity squared plus 0.4 quantity squared. Square root of that gives me 0.566. So what I'm saying to you is this is going to be 1.6, 0.4, and 1.649. This is going to be 0.4, 0.4, 0.566. Now, could I find the angle? Yeah. Sure, this angle is the same as that angle, and I can say tangent inverse of 0.4 over 1.6 That'll give me the angle, and I can do the same thing on the other side. Correct? But I gotta get you started on dealing with things by using slopes. Because the higher up you go in your classes, the less and less we do angles. We start doing more slope, slope, slope. Okay? So I'm going to do this problem, and I don't care how you do it right now. I really don't. But I'm going to do this using slopes. Now remember, cosine of theta is going to be adjacent over the hypotenuse. There's the adjacent, there's the hypotenuse. So 1.6 divided by 1.649 will be the cosine of the angle theta. Agreed? So I don't necessarily need the angle, I just need the slope. And that's what I'm going to use. So, some forces in the x equals 0, positive to the right. What have I got? Well, this has a component this way, and a component that way. Notice the head to tail, you never get away from that. So I'm going to have FAC cosine theta, right? Minus FAB cosine alpha must equal 0. Or I could write it FAC times 1.6 over 1.649. That is cosine theta minus FAB times 0.4 over 0.566. This is cosine of alpha. So instead of writing this and finding the angle, I can do this. They're the same, is what I'm trying to tell you. So this is going to lead me to FAC is equal to 0.728 FAB. Great, box it in, that's equation 1. Didn't get an answer, it's okay, don't panic. Some forces in the y equals 0, positive upward. That's going to be FAC using slopes only times 0.4 over 1.649 plus FAB times 0.4 over 0.566 is equal to 147.15, or minus 147.15 equals 0, same thing as saying equals 147.15, right? This is going to reduce down to 0.243 FAC plus 0.707 FAB equal to 147.15. There's equation 2. And using the method of substitution, which you learned back probably in 8th grade for crying out loud, I'm going to dump this value in for here, leading me to one equation, FAB. Solve, you will get FAB is equal to 166.46 newtons. Take this value, dump it back in here, and I'll have FAC equal to 121.18 newtons. Awesome! Love it! Except I didn't ask you for the forces, did I? What did the question ask you for? Hey, give me the unstretched length. Didn't ask you for forces. This is where good old Hooke comes into play and says, oh, besides equilibrium, I need to go to Hooke. Hooke says FAC is equal to KAC XAC. That says XAC is equal to FAC divided by KAC, which in this case is 121.18 divided by 1500, which is the K value given in the statement of the problem. What? KAC, XAC, Hooke's law. This is going to give me AC 0.0808 meters. FAB is equal to KAB, XAB. That's going to give me XAB is equal to 166.46, which is FAB divided by 1250. That's going to be 0.133 meters. Hey, if you give me those, I still take off points. What? Why? What did you just find?
The extension.
The amount of deformation is, it does not give me the unstretched length. It gives me how much the weight deformed it from its original shape. That's not what I asked you for. I asked you for the unstretched length once the weight has been removed. Unstretched length now, delta AC initial is equal to 1.649 minus the 0.0808. That's going to give me 1.568 meters. Delta AB is going to equal to 0.566 minus 0.133. That gives me the 0.433 meters. That is the answer I want. So remember, give me what I want, not what you think I want. Give me what I want. And then ask you to find me the force. You needed to find the force, so you can apply Hooke's law to find the amount that the springs were deformed. Again, that's not the unstretched length, that's how much they were deformed due to the weight. The unstretched length is the 0.1568 and the 0.433. Bingo, bango, done. Thanks for playing. Next problem. Questions? Anybody have a question? Yes, my son. Do what? The only thing is, then you have to convert the 1250 to millimeters, because it's newtons per meter. I don't care. You can leave it at 1.568 meters. I knew you wouldn't like it over there. I could have figured that. I could have told you that. So why are you here again? Just because you missed me? Or did you miss Carter? You see her quite often. How's her boyfriend? You didn't? You're not sure? You haven't seen him in 2 months? Does he know you're sitting next to her right now? Oh! Should I tell him you got some competition? No. Carpenter's like, hell no! We're just friends. Friends with benefits. I'm just wondering, you know, who knows? Attached, on an incline, attached to 3 springs. But could I not take the 2 springs in parallel, get 1 spring which becomes in series with the other spring and make it 1 spring? So it doesn't matter how many fucking springs I put here. It can all reduce to 1. Agreed? Every single problem I give you can be reduced to 1 freaking spring. So when you sit there and go, I don't know how to do the problem you put on the test because there was 10 springs. Who gives a shit? Take all the 10 springs, reduce it down to 1. That you can do. We've given you the tools to do it. Now, first thing I see is a block on an incline with a spring, and then I see a bunch of pulleys. Yes? I know how to deal with that. If I knew this weight, I could find all the tensions coming across. Correct? But I don't go that way because I'm asked to find the weight of block B. Okay. So, 150 kilogram block was the first thing you think of, right away. Convert to newtons. Now 150 times 9.81, bang, bang, bang. That's the first thing that comes to my mind. That's the first thing that should come to your mind. It's held in equilibrium. Equilibrium, big, nice word that in my mind says, hey, some forces in the x equals 0, some force in the y equals 0. This says I got to multiply by 9.81. Notice how as I read the question, I'm starting to decipher it and lead me to a solution. The unstretched, spring has a K value of 1600. That tells me, hey dude, don't forget Hooke's law. That's what comes to my mind when I see these things. I'm literally putting in red the things that pop in my head as I read these freaking questions. The unstretched length of the spring is 200. In the position shown, the length of the spring is 400. So what did I just give you here? Circle this, circle this. This says x is equal to 0.4 minus 0.2, which is 0.2. Notice, I'm in essence starting to solve the problem without having put much down. And a lot of times I don't put these things down on paper. They're in my head as I go through. I'm only putting them down so that you can see physically what's going on in my head as I read the damn question. Right? Next, tell me the weight of the block B, tension of the cable, C, the normal force. What the hell? That's the first time we've heard that word. What is the normal force? You're sitting in the chair right now. If that chair does not push up on your butt the same weight that you have on it, then you're going to be on the floor. So the normal force is the force that the chair is pushing up against your butt. So here, the normal force is the force that the incline is pushing up on the block. If it doesn't push up, then the block falls through. Okay? That's the normal force. I am going to draw a free body diagram of this. Notice, I touched here, I basically touched here, and there's a weight. So, free body diagram, block. Now remember, these are all particles, but I'm going to give it a kind of a shape, but I'm not putting any dimensions on it. I'm going to show a normal force, and that normal force is perpendicular to the surface. There's the surface, dashed in red. I'm going to show some sort of tension. I'm going to show some spring force. And by the way, I know what the spring force is. Spring force is K times X, 1600 times 0.2. That's 320 newtons. So I already know what this guy is. Due to Hooke's law. Now, if you're sleeping for a second, pay attention because this is important. Anytime I see a incline of any kind, what I tend to do is I tend to tilt the coordinate system like so. So I make my y perpendicular to the incline, my x parallel to the incline. Okay? Now, could I use a standard xy? Sure, I can, but by tilting, I avoid a lot of cosine signs. Right? Because the normal force is along the y. I don't have to sit there and say normal force cosine alpha, cosine, or sine of alpha. The tension is along the x. I don't have to say t cosine alpha, sine alpha. The spring force, 320. I don't have to say 320 cosine alpha, sine alpha to get the x and y components if I were using the standard. Right? So I'm avoiding all that bullshit by tilting the coordinate system. The only thing that I have to do, here's the weight, which I know W is equal to 150 times 9.81. That's 14715, right? Or 0.5 newtons. The one thing that will have to have a cosine sign will be the weight, because it's not along the y or x. It's straight downward. And this angle right here is the angle of the incline, which is 30 degrees. You can prove that that angle is 30 by doing a little geometry. So do a little geometry and make sure you understand how I got the 30. I'm telling you for a fact, which can be proven by doing geometry, that angle between the y and the straight down weight is 30 degrees. So now I come in and I say, hey, some forces in the x equals 0. Please notice how I tilted the coordinate system positive, because every time else I've been doing this, because it's been horizontal. I now rotated the coordinate system, and you can do that anytime you want, as long as you maintain x and y being 90 degrees to each other. And I have maintained them at 90 degrees, I just rotated them to make my life easier. Minus 320, that's this guy, plus tension, and there's a component here. There's a component right there in the x, which is headed downward. So that's got to be a minus 147.5. But it's got to be the sine of 30 equals 0. Take a second, make sure you understand where I got all these things. The free body diagram, it is a effing big deal. That's what I call a free body diagram. Because it's accounting for all the forces. What I see here, I'm going to put in these equations. I see a downward minus 320. I see an upward positive t. I see a green downward component of the weight minus the weight. Well, this is one equation, one unknown. Damn, that's easy. T is equal to 1055.75 newtons. Fantastic. Some forces in the y equals 0, perpendicular, positive. Here's the beauty of tilting the coordinate system. These guys are in the x. They don't come into play at all. Had I used a standard coordinate system, the regular x, y, horizontal and vertical, then these would have components in my damn y equation. Now they don't even appear. Fantastic, I love that. Add is n, and then I have a component of the weight headed this way. There's my head to tail, minus 1471.5, cosine of 30 equals 0, n is equal to 1274.36 newtons. You asked me to find the tension, I did. You asked me to find the normal force, I did. The only thing I have not done is found W. Okay. Here you go. Here's your damn W. If this is T, that's T, that's T, that's T, that's T, this has to be 2T. Does it not? Which means if I draw the free body diagram of this weight B, I'll have this, and I'll have 2T. Some forces in the y equals 0, positive downward. WB minus 2T equals 0. WB is equal to 2T, which is 2 times 1055.75. That cable tension has not changed. WB, therefore, is equal to 2111.5 newtons. Done. Yeah, I got you.
Okay, that.
How about that? Yes, sir.
Could you explain what the system
pretty self-evident. T, 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 T. And if you look at the last pulley, I got T up, T up. What has to be balanced is 2T downward. Yes? What? Throw your ass off. Isn't that a beautiful thing? No. Yes, sir. What 30? 30 degrees is from the angle of the incline. Do geometry, it tells you it's 30. Oh, geometry, my boys, geometry. This is the y-axis. That's 30. That's 30. That's 60. If I have something that's perpendicular, that's going to be 30. That's going to be 60. Then it just alternates 30, 60, 30, 60 as I go around the circle.
All that you know.
Of course. What's that? I scare you? What can I say? No, I just work hard at it. I'm no smarter than you. I just work harder than you. For a longer time than you. But you have the capability just as much as I have the capability. You just tend to put it in different places. I put it in my work. And when I was sitting in that shoe that you're in right now, I worked my ass off. When I mean I worked my ass off, I worked my ass off. I studied and studied and studied and studied and studied. I study 6:30 to 10:30 or 7 o'clock to 11. I go to sleep. I wake up at 4:30. I start studying again before class. Because during class, I want to know what the fuck the teacher was talking about before I get there. I read a lot. Not just the textbook I was given. I went to the library, 6th floor of the library, 5th floor of the library, wherever it is. A bazillion statics textbooks, a bazillion dynamics books, a bazillion thermal books. Grab a book and I started reading it. So I put in the work, I put in the time, I put in the effort. You can do the same thing. Some of you will put the same effort and you'll get the A. Others will give me a half-hearted effort and you'll get to possible C. Not a matter of intelligence, it's a matter of how much you're willing to work. Every single one of you is an intelligent human being. You wouldn't be here otherwise. The only difference is I wasn't lazy. That's the difference. I was not lazy. All I did was I delayed my gratification till later, put in the work. Once I put in the work, then I started reaping the benefits of that. But your generation wants the enemy. Doesn't matter? Okay, it doesn't matter. It doesn't matter. You want to choose positive upward, go ahead. You're going to get the same answer I got. What was your question? Yeah, when was the first calculator?
First calculator was the TI Caltech.
Yes?
1957, but
Yeah, but that wasn't when it was available to the mass.
Mass produced was 1970.
1911?
well, in 1972, it cost a calculator cost $395, even though it was mass produced.
In 1972, it cost $395. Now, let me tell you what. In 1972, okay, that calculator is probably about as powerful as your TI 30.
A4.
You know, the little TI 30s that don't do a whole lot other than multiply, subtract, divide, line, cosine, sine, blah, blah, blah. That's it. So it couldn't do what the TI-84 could do. And at the time, it was $395. And back in 72, gas was probably about, 60 cents a gallon. I remember when I was a little boy and it was 19 cents a gallon. And you go to the gas station, they fill it up for you and give you a set of steak knives.
A what now?
I don't know. I'm being dead serious with you. Yes. Yes, I'm being dead serious with you. Complimentary. Here you go. You filled up our gas and boom. So right there, give me that calculator. This was about the power of the old calculator that cost $395. You go to Walmart, this is about 13 bucks. Amazing. Amazing. Any other questions on this before I move on? What?
So, we found the way the block using like the tension and the cable.
Yep.
The way the block is A and the tension is B. I feel like that's the way to get to the block.
Now, this is. Oh my God! What the hell is he doing to me? Oh, test problem. Oh shit, I never saw this before. You're out the film. Now, let me ask this question. Do you know how to do pulleys? Do you know how to do springs and parallel? Do you know how to do springs in series? Do you know how to do sum force X, sum force Y equals 0? And this shouldn't scare the shit out of you. It looks ominous. Like, oh my God. No. You see this, and the first word I see instantly. Sum forces X equals 0, sum forces Y equals 0. That's what I see instantly. Yes? Now, how many equations do I have to play with? 2. Some X, some Y. Great, fantastic, love it. Now my question to you is, where's the point of concurrency? Because there's always a point of concurrency in equal over 2D. H, there it is right there. Now, when I go here, I touch this, I touch this, I touch this, and in essence I touch that. How many things are there? 4. I can only solve for 2. Sum force X, sum force Y, 2 unknowns. Therefore, somewhere along the line, you must be able to get 2 other quantities to be known. Well, the first known quantity is going to be right here. I say, screw all that. Do I know how to deal with pulleys? So what am I doing? I'm taking what looks like a complicated problem and dissecting into small pieces that are digestible. So here I'm going to say, hey, P. So far so good? If that's P and P, what's this? Huh? 2P. What's this? 2P. What's this? What's this? So coming into this block is 4P, I got 2P, and I got P, and this sucker weighs 1,400 pounds. Sum forces in the Y equals 0, positive upward. 4P plus 2P plus P equals 1,400. P is equal to 200. So, I can forget all this bullshit. I know 200 is coming in there. Yes? Who's not with me? That's me solving for the tension coming into H from the pulleys. That gives me 3 unknowns. Because A, B, C, D, I can group as one spring, right? I can reduce that and get one spring. So I have one force going horizontal to the left. I've got HJ and I got EG. I have 3 unknowns. What do I do? Panic, cry? Hell no! I gotta find something else that will give me a value. Read the question. Hey, find me an equivalent spring for ABCD, knowing the coefficients, the stiffnesses are at the bottom. C, equivalent spring, or B, equivalent spring for E and G. Okay, no big deal. C, the force in cable HJ and the force in equivalent springs in part A. The stretch in springs E and G is 0.2, 0.1. Nirvana. You can hear the angel singing. What's it singing? Hey, springs in series, what do I know about their displacements? This is why you need to know the 3 facts about springs in parallel, springs in series. What do I know about their springs that are in series about their displacements? They have what? That's my free body diagram. Yes? Here is my Y. Here is my X. How many unknowns are in that free body diagram now? Dos. And we're not saying dos X. Just dos. How many equations do I have to play with? Dos. Therefore, I can solve for HJ and the spring force that's going horizontal to the left, which I'm about to do. Some forces in the Y first. Positive upwards. That's going to be FHJ times 4/5 minus 600 sine 20 minus 200 equals 0. FHJ comes out. FHJ is 506.52. What? Doing this algebraically? Put in your calculator. 1/3000 equals 1/6000 equals, add them together, then take the inverse of it. All right. I'm going to say some forces in the X equals 0, positive to the right, 3/5 FHJ plus 600 cosine 20 minus FSP equals 0. Take this, dump it into here. FSP is equal to 867.73. So I saw 4 things coming in. I said to myself, I can apply equilibrium, I can only solve for 2. Therefore, I have to be able to find 2 other quantities. I did. One coming off the pulleys, 200, and the other due to the fact that I have springs in series and I was given their displacements, I was able to find the 600. And therefore, I was able to solve for FSP and HJ. Yeah? K equivalent of the 2 springs, EG. Equivalent. I also need the equivalent for ABC. So K equivalent of ABC is 600 plus 400 plus 500. That's going to equal to 1,500. Now that 1,500 is in series with the spring D, in which case I say 1/K equivalent is equal to 1/1,500 plus 1/, the D is 3,500 Therefore, K equivalent of A, B, C, D is 1050 pounds per foot. That's what part A was asking for. Yeah? Who's not with me? Oh boy. Dang it, dang it, dang it. What else we got? Talk to me. You ready? We're going on to the next problem. What mice is that? Oh. Everybody ready? We're moving. Here we go. Next problem. Next problem is what I call the failure criteria problem. Now, if you're looking at the textbook, usually it has 2 questions per diagram. The first question is going to be straight up equilibrium, finding the forces. The second question says, hey, if the strengths are such and such, find me the largest weight that can be handled. So these are the strengths of those items, A, B, B, C, C, D, and C, E. If you've ever gone fishing, if you want to go fish, usually if you're going to say shark fish, you're going to have a thicker line. So they usually have forces for those lines. Those are called the test lines, right? Same thing here. Each of these have a strength. Now, the way to solve a failure criteria problem is to express all forces in terms of W. Do not go in here and say 300 here, 200 there, 250 there, 260 there. You'll find that one of your equilibrium equations is not in equilibrium. So don't do that. Okay? First thing I'm going to notice is there's a point of concurrency at each place. So, free body diagram at B and then a free body diagram at C. Here it is. I have a force FBC. I have a force FBA. I have a weight downward W. Coordinate system. Same old standard XY, damn it. I don't have an incline. Angle. The angle are 60 here, 30 there. Free body diagram here. I got some force FCE this way. I got some force here FBC that way. And I'm going to show this solid member pushing up DC. I can draw pushing down or pulling. I'm going to draw pushing up, which means DC is in compression, not tension. Pulling at a joint, you're in tension. Pushing up, you're in compression. Put in your coordinate system. Luckily, the coordinate system is only one, and that's XY. Angles. Well, you're told here this is 45. If that's 30, that's 30 because of alternate interior angles, 30. Now, just write your equations of equilibrium. Great, let's do that. Some forces in the X equals 0 positive to the right. FBC, cosine 60, minus FBA, cosine 30, equals 0. FBC is equal to 1.732 FBA. That is equation 1. Great. I got you. What's the goal in a failure criteria problem? The goal is to get all forces in terms of the weight, because I want to find the largest weight I can carry. What?
Instead of 60 or 30.
Where?
Yeah, that's what I'm saying.
What?
For FPC is supposed to be 30 plus.
Oh, shoot.
I mean, it's supposed to be 60 not 30. That's what she did.
Where are you at?
Right there, in the freeway area.
On the right side.
Other one. What did I do? Oh, I see. You're right. Yeah, this should be 60. Very good. Thanks for catching that error. Some forces in the y equals 0 positive up. That's FBC sine 30 plus FBA sine, oh shit, that's 60. Sine 30 minus W equals 0. Remember, we're still obeying the parallelogram rule. This has a component this way and a component that. There's the parallelogram rule being obeyed. Component this way, component that way. So, this is going to be 0.5 FBC plus 0.866 FBA equals W. That's equation 2. Now, you do what you did back in 8th grade. I got 2 equations, 2 unknowns. Instead of X and Y, I got BA and BC. Big deal. Take this, dump it into there. You have 1 equation in BC. If you solve this, you'll find that FBC is equal to 0.866. Oh, sorry, wrong place. Dump in here, not there. You'll get FBA. Yeah. FBA is equal to 0.5 W. Take this, dump it in there. I'm going to call it equation A. Dump it in here, and I'll get FBC in terms of W. 0.866 W. Take that FBC and put it here, and you'll see that FBC is equal to 1.181 W. What was my goal? Get every force in the system in terms of W. Now you apply the failure criteria. What do I know? I know AB has a strength of 300. AB is this, so I got 300. Yup. 300 is equal to 0.5 W. W is equal to 600. BC has a strength of 200. 200 is equal to 0.866 W. W is equal to 230.94. So what's the largest W you can carry without a failure right now? 230. Right? And 2 more. CE is 250 is equal to 0.612 W. W is equal to 408.49. Lastly, 260 is equal to 1.181 W. W is equal to 220.15. W max, therefore, 220.15. That's the largest you can have based on the strengths given in the problem. Okay? That is a failure criteria problem. Please do not put those forces, the strengths, in and try to solve an equilibrium function. One of your equations will not be in balance. See you tomorrow.